Hi everyone, due to my business trip to Seoul, so today I will just show you some important process steps to fabricate state-of-the-art MOSFET, FinFET case. This is one example I have created for you, and here you can see this plane is just artificial one that does not exist, and this gray one is actually corresponding to the silicon. I guess that this thickness is given as 150, but this is just an arbitrary number. But important one is here, this top view, you can see that the scale, x directional scale is corresponding to about 108 nanometer, and this vertical direction is corresponding to 272 nanometer. This is a wafer top view, and you can have quite a simple, just a silicon. Of course, in reality, we have here and there silicon, but that is out of our processor emulation, and we will just consider only part of it. Now we wanted to pattern this silicon, and in order to make any pattern on this structure, so we have to prepare a complicated process. So let's just start. You can see now we have a little bit different material here, shown as deep blue, and this is corresponding to, in my example, corresponding to the oxide. Here you can see this is a PET oxide, and its thickness is just 5 nanometer, and this is a very thin one. Now we add this silicon nitride region called as hard mask. So in this case, we don't have any patterning on it. It is just deposited globally. So now we have a very flat structure. So compared with the other material, this silicon nitride is regarded as a rigid one. So it is used as so-called the hard mask. Hard means that this can resist against any kind of external damaging. Now, on top of this hard mask, we add another silicon layer called as mandrel. Um, so that is just used for certain intermediate structure to eventually make a pattern on this substrate. They will be gone eventually, but they are introduced just to make a certain pattern. Now we have a mandrel, and now we have to make a pattern on the mandrel. So for that purpose, we introduce a certain kind of a mask. Here we have a certain boxes, rectangular boxes, and these boxes are saved from any kind of etching. So using this mask named as mask pin, I will try to pattern the mandrel. Okay, by using this mask, now when we do the etching process, the one covered by this mask was saved from the mask is now still remaining, and other part which is not covered by mask, that is actually etched away. Now we have a certain form of lines, horizontal lines, where we have certain remaining silicon. And this etching process is ended by this reaching at this silicon nitride, because we assume that between silicon and silicon nitride, they have such a huge difference in their selectivity, and if we can etch silicon, then we can only etch silicon. We cannot etch this silicon nitride. Now we have a pattern, and you can see that this uh, distance is not actually corresponding to the desirable value of our FinFET. So we have to find out certain way to make an even thinner pattern. Let's just to do it together. For that purpose, we intentionally introduce this step called as a sidewall. And sidewall, as you can see here, they share the same deep blue color. It means that this is corresponding to silicon dioxide. Silicon dioxide is deposited, but shape seems to be a little bit different in this case. In this deposition step, we deposit our silicon dioxide isotropically. Means that previously we had a certain remaining mandrel, and if we deposit it in an isotropic way, then we will have just on top of this mandrel and on top of this bottom silicon nitride. But you can see that here there are certain silicon dioxide even deposited from this vertical wall. So the depth grown depth from this one, deposited depth from this top surface, and depth from distance from this vertical side wall are the same. So now we have a very beautiful graphs isotropically covering this mandrel pattern. This is the key point to make even shorter channel. Now we have this sidewall. So let's just continue to the next step. Although previously we deposited our silicon dioxide in on isotropic way, but in this case, when we take the etch process, we just took anisotropic etching process. So it means that previously we had this shape, but this part is saved because previously we had a certain amount of silicon dioxide covering in this part. So only on top and on this bottom part, they are eliminated. Point is, now we have the remaining sidewall, and the thickness of this sidewall is the original deposition depth. So that was 7 nanometer in my case. So now, although we start from quite a thick structure, which is given as mask patterning, but the thickness of this structure, so sidewall structure, is not controlled by this distance, but deposition just precisely control the distance between these 2 points. Now only silicons are etched away, so now you cannot find anything corresponding to the mandrel. Mandrels are gone. And how can we save our hard mask shown here? Is it because when we etch away this silicon, once again, silicon nitride and silicon have quite much different etch rate, so it is not damaged by this silicon etchant. So now we have very clear pattern shown here, and its thickness is just given as 7 nanometer. Wow. So they are separated in a certain distance, but point is their let's say their width is determined by deposition depth 7 nanometer. They will be the basis of the FinFET. Okay, but please note that this is just silicon dioxide, and actually what we wanted to do is make this thin pattern in this silicon substrate. So how can we do that? It can be done by changing the etchant. So we do an anisotropic etching. So only vertical directional etching is performed. And fortunately, this part is covered by silicon dioxide. So it is not etched away. They are saved from this um, etching process, and only the part which was not covered by this silicon dioxide that is etched away. So now we have very well transferred pattern to this hard mask. So they, please note that they are hard, so they are mechanically rigid. Then now this PET oxide is also etched by changing the etchant for silicon dioxide, and now we have this silicon surface eventually exposed. So now we wanted to make this pattern. Then now we can etch our silicon. So in order to make the combination of mechanical stability and also good short-channel immunity, we intentionally perform such kind of two-step etching. One is almost upright fin, and after that to support this fin part, which will be eventually become the channel, we introduce the tapered angle for our subfin structure, and beneath of it we have just plain silicon substrate. So now we have a well patterned silicon fin, and now we have to do the next steps. Well, although we have made these fins, but they should be isolated. So in order to introduce isolation between them, so we have to introduce a certain insulating. For that purpose, we first of all introduce so-called gap fill, and just to introduce a lot of silicon dioxide layer and make it just planarized. So behind this silicon dioxide layer, we have already fabricated the internal structure fins, and we will try to reveal them. First, by using the chemical mechanical polishing CMP, so silicon dioxide is removed. So from the top of this structure, we make CMP, and after that, once it arrives at a different material, called as here given as silicon nitride, it can detect the arrival of new material. Then we can start the polishing step. So we will have quite a planarized structure as shown here. Here we are looking at another mask, name is mask active, and you can see that these two islands are corresponding to active parts. So here we have a NMOS part, and here we have a PMOS part, and these parts are not used for active devices. So although here we have fins, these fins will be removed. So that will be done by etching process later on. So using the active mask, we save the active regions, but instead of that, for the non-active regions, um, mm, etch the nitride. So subsequently, of course, we will also remove this fin. So let's just have a look at. As you can see here, we also simply etched the PET oxide. Now this silicon fin is exposed to the air. Now, by etching the silicon only, now we can completely remove the fin in non-active regions. So here we have active regions which is saved by our or protected by our hard mask, and here we have previously fins, but that is now eliminated by etched away. Now we have for certain reasons we have active fins, and there is nothing else. So this procedure is called as a fin cut. So unnecessary fins are eliminated. Then by removing the silicon dioxide, now we have only silicon fins. Yes, they look really beautiful, and we have the fins whose thickness is about 7 nanometer, which is originated from the deposition thickness of this layer, and they are placed in the position we wanted to have active regions. And for others, we don't have any other fins. Yes, that's what we wanted to have. Now we introduce the line oxide, which is relatively thin, about 2 nanometer, just to protect our silicon fins here. Yes, they are covered in an isotropic way. So line oxide, yes, this is corresponding to the line oxide. And we introduce STI, shallow trench isolation. So previously there was only um, line oxide, and by depositing also isotropically, now we have STI. But of course, this the purpose of this STI is not covering the entire structure. We have to make some partial isolation, so we have to do that. So we do the CMP once again. So maybe you feel that we have seen the similar structure previously. Yes, previously when we had everything here, there was a certain kind of a planarized structure. Previously, the the hard mask top was used as the CMP stop layer, but now it is a little different because previously there was equally placed fins, but now we have some parts, some non-active parts without fins, and now we have active parts where we have fins. That is different. Now STI is eliminated, but in this case we still have a silicon nitride hard mask. Now it has been done, it's a job, so now we have to remove it. It can be also selectively etched away, so now we have the structure, the wanted structure where we have fins and without any hard mask, and the entire structure is covered by this STI region. So where do we have a STI? Yes, this is the STI. By further etching the silicon dioxide, now we can finally reveal this silicon fin. So here we have a sub fin, and that is still isolated by this STI, remaining STI. Yes, and now we have a well revealed silicon thin layer, and its thickness in this case is 7 nanometers. So this is the case. So as you can see once again, if we take the top view, we can see the part 4N MOSFET and part 4P MOSFET, and there are two fins, and their isolation is done by this STI, and still we don't have any kind of structure like a gate or source and drain. That will be done later. What we have done up to now was just to fabricate the fins in uh, our silicon substrate. Now we will do some patterning for gate. But before doing that, in order to protect our very precious this silicon layer, first of all, we introduce so-called dummy gate oxide. So this is quite thin, like about 2 nanometer, but by depositing it, now our silicon fins are protected by subsequent etching processes. Dummy gate is usually made of polysilicon, so in this case, both of crystalline silicon and polysilicon are shown with the gray color. So this is corresponding to the polysilicon gate. Of course, there is no patterning at all right now. It is just isotropically deposited. So we have a certain up and down here. So we will do certain CMP. So the planarization by CMP is done, and the assumed distance between this fin top to the dummy gate top is about 90 nanometer in this case. We will use two layers of a hard mask, which first one is silicon nitride, then later oxide, silicon dioxide, and first one is nitride. We have deposited 50 nanometer thick one here, and also deposited the second layer, oxide layer. Its thickness is said to be 35 nanometer. But anyway, now here we have a dummy gate and two layers of hard mask. Now we introduce the mask for our dummy gate pattern. So in this case, you are looking at the cell boundary here, and this yellow, thicker yellow one is corresponding to the full dummy gate, whose length is given as 18 nanometer. And you are now looking at here and there, just half of it, because there is a mirror site here and there. So overall, we are drawing just 18 nanometer thick lines in vertically. Please note that previously we had drawn our fields in a horizontal way, but now we have vertical lines corresponding to the dummy gate. Of course, this is just a mask, and we have to pattern it using our photolithography patterns. Using the mask pattern, we have etched away first the top silicon dioxide hard mask. So as you can see here, that is etched away, and this is corresponding to our pattern for full dummy gate, and this is a half one. And of course, we wanted to transfer it to this polysilicon layer. Right now, only top hard mask is patterned. Of course, this already patterned silicon dioxide, this lower part, silicon nitride, can be well patterned. So now our polysilicon layer is exposed to the air. Quite naturally, we can also etch the polysilicon dummy gate, and now we have the fins here and there, which is uh, exposed to the air. Of course, it is covered by our dummy gate oxide, but anyway, it is not far away from it. So now we have from the top view, this is the dummy gate, and this is another dummy gate, and between gate and gate, so these are places for our later source and drain. If we make our source and drain directly in this etched part, then actually there will be no separation between source and drain and dummy gate. So in order to separate them, we have to introduce a certain dielectric material. It is once again called as a sidewall, and usually we use a little bit different dielectric material, silicon oxycarbon nitride. So previously, it was the situation after dummy gate patterning, and now we introduce this sidewall. So between this dummy gate, so we magnify between this dummy gate and here, the place for source and drain, we have about 6 nanometer thick separation by this spacer material. So we look at this one here and there. This will be NMOS source drain, NMOS source drain, PMOS source drain, and PMOS source drain. And this spacer will remain at the end of our process. It is very interesting. Even we can find some etchant which has good selectivity of silicon oxycarbon nitride over other dielectric materials, and we um, etch this silicon oxycarbon nitride anisotropically. So previously there was a certain sidewall, but that sidewall is now completely removed in this hard mask part. But still, we have here sidewall remaining. So our dummy gate is still separated by the sidewall. And still, yes, the isolation is good. And now the next part is we have to introduce a certain source and drain. But before doing that, here we have a dummy gate oxide that should be removed in this case. Now you can find that this dummy gate oxide is etched away, and now the silicon fin is now revealed here, and there you can see that they are these gray layers are found, and slightly also this STI part is etched away, but it's completely okay. So now we are ready to do certain part of a source and drain formulation.